Well, you came back to learn more, and that's great. In this video, we are going to talk about signed integers or how signed integers are represented or stored inside computer, okay? Working with unsigned integer was quite straightforward and it was not really difficult, okay? But with signed integers, yeah, we have to be just kind of careful and we have to just use other strategies. So for now, just simply we have to remember one thing, okay? Mostly, yeah, we can just work with 8-bit integers, 16-bit integers, whatever we are just working, okay? The leftmost bit is MSB, most significant bit, and that is just going to be very important for this unit, okay? So let's see what it is and how it works. So overall, computer only uses ones and zeros, okay? So there are no minus sign button in memory, okay? That, yeah, there should be something inside processor or inside RAM that, yeah, if you change that, it becomes negative, okay? So only that is 0 and 1. So we have to just kind of store that positive or negative as well as 0 and 1, and we have to just kind of make the computer understand in that way. So an 8-bit byte can hold 256 unique patterns, yeah? If we want to store only positive or unsigned integers, that will be 0 up to 255, which will just simply make 256 different numbers or integers. But with signed integers, if you want to store, so yeah, we have to just kind of shift that from negative 128 up to positive 127. We can just store that again it will be just simply 256 different characters, okay? So simply the range is changed, but the number of unique patterns is the same, from negative 128 up to positive 127. Again it will be 256 different unique patterns, okay, that we can store inside 8-bit of memory. See, MSB most significant bit, why that is kind of very important for us, because we can just use that as the sign bit, okay? So if that is 0, it means our number is positive. If that is 1, it means our number is negative. So here this is just negative, and yeah, we have gotten 1, 2, so we do not have them, yeah? We have gotten 1 4 and 1 8. 4 plus 8 will be 12, and we have gotten 1 16, okay? So 16 plus that will be 28. So this is negative 28. If this loss significant, if it is 0, then yeah, we can say it is positive, okay? So the same thing here, see, positive 28, our most significant bit, that is 0, so it means it is positive, and here that is just kind of negative, okay? And this is our first bit, or that is just a part of the number itself, okay? So 0 means positive and 1 means negative. It makes perfect sense to humans, but for a computer CPU, this method is fundamentally broken, okay? So we can just use this, but yeah, again, we will have some problems, and we will just talk about the solutions for those problems. But right now, see the flaws of a sign in magnitude. Here, what is the problem with this method, okay? Let's see what are the problems, okay? So the first one is we have gotten 2 different patterns for 0, okay? So 8 zeros, that is also 0, and 1, then after that 7 zeros, again that is 0. So 1 is just kind of positive 0 and negative 0, and 0 cannot be positive or negative, okay? So that is just only 1. So that is just one problem that we have gotten here, and in order to resolve that, computer will just when working with 0, computer will just need to perform many additional operations, okay? That will just simply slow down the work. So we do not use this much with CPUs, okay? Then the next one, yeah, that we have gotten just some math failures, okay? For example, yeah, here, if you just combine positive 28 and negative 28, it must be 0, okay? But see what do we have here? So yeah, 0 plus 0 will be 0, 0 plus 0, again 0, 1 plus 1 will be 2, which is 0, and 1, okay? 1 will be just kind of there, okay? And 1 plus 1 plus 1, again, just that is 3, which is 2 ones, okay? So again, we have gotten 1 there. So again, 1 plus 1 plus 1, it will be 2. So 1 here and 1 there. So again, yeah, 1 plus 0 plus 0, 1, then 0 plus 0 is just 0, and 0 plus 1, again, just simply it becomes 1, okay? So see, that is a system failure. Right now, we have gotten a negative 56 as a result, okay? So it does not really work well. So adding positive 28 and negative 28 should equal 0, not a negative 56. So that is just the problem here, okay? That's why we are just not using this method with the CPU. So what is the solution? What should we do, okay? So engineers or computer engineers have created some other methods to store that, which is just known as two's complement, okay? The standard computing approach for this. Okay, we will just study how does two's complement work for positive and negative numbers, and what benefits does it have, what problems does it solve. So the engineering solution, okay, adding by subtracting, okay. So if we just use this method, okay, it will just simply solve some of the problems, okay. Modern CPUs process subtraction by executing a specialized form of addition, okay. So subtraction inside computer as well, it is done with the same operations of addition. And why that is good? Because this, yeah, you do not need two different pieces of hardware for subtraction and addition, okay. Before with the sign bit, we will just simply need two, but here just we with the same we can work, okay. Two's complement makes this possible without adding expensive or separate physical logic. We will study that again, okay. Simplified circuitry allows the computer logic unit or ALU to use the exact same adding hardware for subtraction operations. And unique 0 eliminates duplicate 0. 0 is exclusively represented as 0 0 0 0 0 0, okay. And mathematical soundness, operations such as a minus b translate seamlessly into a plus negative b, okay. So we do have the negative b, so in order to just perform this subtraction, we can just do that addition. So again, we do not need two different hardware parts, okay. So the three steps conversion logic. Now, how can we just simply change the binary numbers or negative numbers to binary? So that is quite easy, okay. First of all, you will write the unsigned baseline, whatever, just for example, you want to store negative 10, you will have to just write the positive 10, write the positive of that number, okay. Then after that, binary complementation, flip them, change zeros to 1 and ones to 0. So 0 is changed to 1, 1 is changed to 0 in all of them. Then finally, what? Add 1 to the flipped one. So now this is the flipped, and we are just adding 1 to that. So we will just get something like this. Now in 2's complement, this can be just read as negative 10. Okay, so always when you are just told to change a negative number to binary in 2's complements, so that this three steps you have to follow. See here, we want to store negative 69 into 8-bit 2's complement binary number. So first of all, we will write the positive 69. Okay, so this is positive 69. Okay, 1 plus 4 plus 64. So that will just make it 69. Okay, then step 2, flip that. Okay, 1 is changed to 0, 0 is changed to 1, 1 to 0, 0, 0, 0 to 1, and 1 to 0, and 0 to 1. Then after that, add 1. So I'll just write 1 here, and I'll just simply add that. 0 plus 1 will be 1. 1 plus 0 will be 1. 0 plus 0 will be 0. 1 plus 0 will be 1. 1 plus 0 will be 1. 1 plus 0 will be 1. 0 and 0 will be 1. And 1 plus 0 will be 1 again, okay? So again here in this method as well, this most significant bit again just simply signifies the positive or negative. Okay, here it's 1, so it's negative. Okay, so this will be just simply our negative 69 in 2's complement. Okay, so that is just the three steps that we have. You can just take any other number and just change that with the same steps. Now in operations, okay, addition or subtraction, this will just kind of make our life much easier. See here, let's just do math, okay. Positive 28 and negative 28. in sign bit, that created a problem. But let's just see here, does it solve the problem or not? Okay, so we have gotten positive 28. In negative 28, just we changed the same way that, yeah, we told you those three steps we have worked on 28, and we have just gotten to this pattern of zeros and one. So this is our negative 28 in 2's complement. Now let's add them together. It should be 0. It should not be just any other number. So yeah, that is okay. See, 0 plus 0, 0, 0 plus 0, 0, 1 plus 1 will be 2, so 0 and 1. 1 plus 1 plus 0 again will be 2, so 0 here, 1 there, okay? Then 1 plus 1 plus 0 will be 2, so again 0, 1, so 1 plus 1 again 0, 0, 0, okay? We have just gotten the last bit which changed to 1, and because just simply it is 8 bit, so the ninth bit we cannot have, okay? So the ninth bit will be just ignored, and that will be just deleted, okay? So we will have 0, 0, 0, 0, 0, so that our problem is solved. Positive 28 and negative 28 just change to 0, okay? So because the hardware is strictly limited to 8 bits, the ninth overflow bit is discarded. The result is a perfect 0, 0, 0, 0, and the math works seamlessly. And reversing back, okay, back to Denary. Now if we just simply want to change from binary to Denary, okay, so in this way, if our lost or simply that most significant bit, and this is just in 2's complement, okay, in 2's complement, this lost one, 2 to the power of 7, which is just 128, it is just negative 128. It means if we have just, if this is 1, so we'll have a negative 28 there, and just the other numbers, they will be positive, and we will just add them together to just receive our number, okay? So place values, if the most significant bit is a 1, it acts as a negative anchor. You subtract, okay, 128, then add all other active positive places values as normal. So now that is just how we change from 2's complement to Denary, okay? So in the exam, they might just give you some binary patterns, and they just simply tell you that, yeah, this is in 2's complement, change it to Denary, okay? So that is just how you do that. Let's just work an example. See here, now we have gotten calculate the Denary equivalent of 2's complement, 1 1 1 0 0 1 0 0, okay? So we'll just simply write this 1 2 4 8 16 32 64, and in signed values that will be positive 128, yeah, but right now it's 2's complement, so that will be negative. So we have just gotten negative 128 plus 64 plus 34 plus 4, okay? So this will just simply make 100, and negative 124 plus 100 will just simply give us negative 28. So this is negative 28 in 2's complement. And just once again talking about the range, so if it is just unsigned integers in 256 unique patterns which we can store in 8-bit, 0 up to 255, okay? So 0 and 1 2 3 up to 255 will just simply make 256 different patterns, okay? But in signed integers, we can just simply store negative 128 up to positive 127. That will just simply make 256 unique patterns. And outside this range, if we just want to store any value, that we will just have overflow problem, okay? So that's it. You can just read this by yourself. So see here, identification and range, okay? So the MSB test, identify which are negative instantly. So negative, yeah, 1 and 1. We just told you that if MSB is 1, so this is negative, okay? So here these both are negative and these both are positive. The boundaries, okay, state the maximum range of an 8-bit signed integer, okay? So lowest will be negative 128, okay? So that is 1 0 0 0 0 0 0, okay? And highest is positive 127. So see, that is kind of positive, and after that we have gotten 1 1 1 1, which makes 127. So that is just boundaries. You have to just know them by heart, because yeah, you will have just questions in your exams from this. Mini mock calculation. Here is the binary bit pattern for a signed integer in 2's complement format. Okay, so we have gotten 1 1 1 0 0 1 0 1. Yeah, convert the binary pattern to denary. Okay, so simple, because question has told us it is 2's complement. So this first one, that is negative 128. Okay, plus 64 plus 34 plus 4 plus 1. So that is kind of the method, and adding them together, that will be just negative 27. So this bit pattern is for negative 27. Okay, examiners award marks for working, okay, this stage. If you make an arithmetic error but explicitly show the negative 128 column setup, use secure method mark. Okay, so one mark you will just get. If your calculation was wrong, then yeah, you might just lose the next mark. So in exam, be careful to write the method and the final result. Okay, and some other questions, multiple choice. Identify the value of the most significant bit MSB used to indicate a negative integer value under sign and magnitude representation. Okay, so most significant bit used to indicate a negative integer. So that is kind of 1. We cannot store a or negative 1 inside a bit. 0 and 1 we can store, and 0 is for positive, 1 is for negative. Theory identification. State the exact range of denary integer that can be successfully represented using an 8-bit 2's complement layout. So that is negative 128 and positive 127. Okay, other questions, negation conversion. Okay, convert the negative denary integer negative 69 into an 8-bit 2's complement binary pattern. Show your working step by step. Okay, so there are some examples. You can just pause the video without looking at the answer, and after that come back to see your answer. Okay, so the first step was write the positive baseline. Okay, so negative 69 you want to change, so positive 69 will be just kind of this. Then step 2, invert the bits. Okay, and change zeros to ones and ones to zeros, and add 1 to it. Okay, if you add 1 to that, then simply you will have something like this. So this is negative 69 in 2's complement. And binary translation, calculate the denary equivalent of this 8-bit 2's complement format pattern. Okay, so again change it to denary. So here again, this most significant, if it is 2's complement, this most significant is negative 128. Okay, so this is 1, so that will be just negative 128. Then after the rest of them. Okay, so that is 2, 4 and 16. Okay, so 2, 4 and 16, we will have just negative 128 plus 16 plus 4 plus 2, that will be negative 106. Okay, so that is just kind of our result. Exam taking tactics for success. Always check the leftmost bit first, because that is just kind of your negative or positive symbol. Okay, so you have to know that. And do not forget to add 1. Okay, and many times in changing any number to 2's complement, students forget that adding to 1. Okay, so write the positive, flip them, and add 1 to that. Okay, without that add 1, it will be just 1's complement, only flipping. Okay, and after that, if you just simply add 1 to it, so it will be just what? It will be 2's complement. Show both plus and minus signs on your paper when you're just writing positive or negative after changing from binary. Okay, so you have to just write that positive or negative to ensure that yeah, your answer is correct, and to just make sure that yeah, you will have your marks. Okay, and remember that trying to represent any value greater than 127 or less than negative 128, okay, within a single byte will trigger an overflow error. So it means that is our range. This is just negative. Okay, this is a typo. And if you just kind of try to store any number outside this range inside 8 bits, you will have overflow error. Okay, for example, you cannot store 129 in 8 bits. Okay, or negative 130. Okay, you cannot store inside 8 bits. And final mastery, the first glance, check the MSB to make sure your number is positive or negative. The next one, okay, the flip engine uh, or the conversion engine. Okay, and that flip an 8 to 1. Okay, that works both way, changing to from denary to binary or binary to denary. Okay, we will just work some examples on this in the next videos as well. Okay, and the ultimate range, okay, 128 to 127, that is just our range. Yeah, so let me just give you some more information about this. Okay, the number is written there, then you will just simply flip them, and after that add 1. Sometimes students make mistakes in this. Okay, changing denary to binary, they think that yeah, this is the opposite of denary to binary. So first they add 1, then after that they flip all the bits. Okay, no, in both situations, yeah, you have to flip the bits first, then add 1. Okay, then you can just simply read. Then the ultimate range, remember that. Okay, negative 128 up to positive 127, that is just simply your range for 8 bits. Okay, and in IGCSE mostly we are working with 8 bits patterns. Okay, so that's it. Wish you all the best, good luck, and goodbye. Do not forget to like and subscribe our channel.